Okay, 6.2 integration by substitution. So this is going to be referred to as U sub, hence the little submarine. Um, deriving the chain rule, right? Let's start with that. If you remember the chain rule, if I wanted to derive something like this, let's see, something inside and outside. Okay, so for chain rule, if I wanted to derive that, we would have to treat the outside as one big old function. So this would be considered u cubed, right? The cubed. So we would derive that, and we would get 3u squared. But then we would have to multiply it by the derivative of u, of the stuff that was in the inside of the function. This is a composite function. It's two functions within one. Basically, x cubed and the 3x minus 2. They're combined, and they make a composite function. So then we would multiply by the derivative of u, which would be, well, 3x minus 2, the derivative of that is 3. Right? So the derivative of the outside times the derivative of the inside. And then simplifying this, it's 9u squared. And before we were actually finished, we'd have to substitute the u back in. Remember, u is just a variable that we're using to help us, to facilitate this process. But it didn't just come out of nowhere. It's not a new variable. It's not the actual function itself. So in the end, I would have to be like, okay, equals 9, and then u was the 3x minus 2, and then squared. And then that would be my final answer. That would be the derivative. Okay, today's lesson is basically taking this derivative and integrating it. So I have to work backwards. I have to figure out, or undo rather, that derivative back to its original form. And that is what anti-differentiation of a composite function is. We're basically anti-deriving something that was derived using chain rule. So let g be a function whose range is an interval I, and let f be a function that is continuous on I. If g is differentiable on its domain and f is an antiderivative of f on I, then, okay, so basically here I have f and g of x, and in my integral, g of x is the inside function, and then here's the derivative of it, because the chain rule works that way, right? The derivative of the outside times the derivative of the inside. And then what we're going to do is we're going to use the letter u. We're going to substitute the inside function with u, and then its derivative is going to be classified as du. Okay, so example 1. So here, first step, look at this and determine what part of this is the derivative of the other part. So and this one's pretty simple to see because it is divided up into two pieces. Okay, the x to the 5th plus 5 and the 5x to the 4th. So I have to figure out which one of these can I derive and get the other. So the original function is going to be u. So which one of these would I derive to get the other? So hopefully you're like, okay, if I derive x to the 5th plus 5, I get 5x to the 4th. So x to the 5th plus 5, that's u. Its derivative is the other piece. Okay, so, but what I want you to do is, I want you to use u, right? Once you determined, okay, this is u, I want you to take this u that you have here, x to the 5th plus 5, and I want you to derive it. So that x to the 5th is 5, x to the 4th, and then the plus 5 becomes 0. And then I'm deriving with respect to x, so dx. Okay, so next would be look at your u and your du, right? And make sure that that is taking care of every single piece of this integral. Okay, so u is taken care of right here. And then this 5x to the 4th is right here. And then this dx is right there. So every single piece of this integral is being taken care of. I am accounting for every single piece. So I'm going to go ahead and substitute in the letter u because I don't want to have to mess with all these numbers. So now I'm integrating. I'm going to replace this with u. And then these two things, if I look over here, these two things are going to be replaced by du. So now this is my new integral. And we have been integrating, so you should be able to integrate u. Okay, just pretend it's an x for right now. Right now this is u to the first power, so to integrate, we would add an exponent and divide by the exponent, right? And then the du, right? Just like when we do any integral, the dx does go away. So here is my antiderivative. And the only step left to do is to actually go ahead and put u back in. U was x to the 5th plus 5, and then plus c. And there's my integral. Okay, example 2. Okay, so again, figure out what is u and then take its derivative. So if I look at this, 5 cosine 5x. Okay, so this right here, the inside stuff. If I derive that, I get 5. So u is going to be 5x. And then I'm going to derive 5x, and it is 5, right? Just making sure, dx. Okay, so what is being accounted for here? So the 5x is right here, and then the 5 is right here, and then the dx is right here. So I am left with, and notice how this time I have limits. So pi over 3, well, you know what? Don't write that just yet. I'm going to have to explain something. Okay, so I'll write my limits last. So the 5, the 5x, and the dx, those are all going to be replaced. The 5 and the dx, that's going to be replaced by du. And then the 5x here is going to be replaced by u. So what do I still have in the equation here? I have cosine, and now u. Okay, because I introduced u into this integral, I have to take into consideration the fact that these limits, the upper and lower limits, they are x's. They belong to the original function when x was in it. So my limits are actually x equals 0 and x equals pi over 3. Yes, do write it. Okay, you don't want anybody to believe that the pi over 3 and the 0 are limits for u, because they're not. They're for x. And remember, at the end, we do put x back in. Okay, so now integrate. So let's see. The antiderivative of cosine is sine. So sine u. And then I'm evaluating it from, let's see, x equals 0 to x equals pi over 3. Okay, so I integrated. I don't need the plus c because I have upper and lower limits. But now I have to replace the u with what it actually is. So sine, and then u is 5x. And then I'm evaluating that. Oh, and now because x is back, I no longer have to write x equals 0 or x equals pi over 3. The integral's done. I'm just left with evaluating. So sine 5, and then pi over 3, and then minus sine 5 times 0. So the sine 5 times 0 is just 0, so I'm just going to write 0. Okay, unit circle time. So 5 pi over 3. Here's my unit circle. Okay, So pi over 3 is right here. It's 60 degrees. I need 5 pi over 3. So 5 times 60, if you want to look at it that way, 300 degrees. Uh, so, this is 90, or pi over 2. And then this is pi, or 180, right? Let me write the pi over 2. Okay. This is 3 pi over 2, or 270. So it's going to be in this quadrant, right? Pi over 3, or 5 pi over 3. It's going to be about right here. 5 pi over 3. And it's 300 degrees. Okay, now, the coordinates for pi over 3. The coordinates here are 1/2 and the square root of 3 over 2. We're dealing with sine, and sine is the y-coordinate. So sine 5 pi over 3 is square root of 3 over 2. But in this quadrant, I'll write it right here. Down here, in this quadrant, my y's, well, my x's are positive, but my y's are negative. So it's negative square root of 3 over 2. And then sine of 0. Here is 0. This is 1, 0. The y-coordinate is 0. The sine of 0 is also 0. Okay. So my answer, negative square root of 3 over 2. Okay. Unit circle. Wonder if she's ever going to give us that quiz. There's no homework today. Let's see. Okay, try it. So go ahead and try it. Pause now, and then when you hit play, I'll have the solution written out for you. Okay, so here I color-coded this. X squared plus x is the u. If I derive that, I get 2x plus 1 dx. And ooh, yes, they are present in the integral. So then I take out the 2x plus 1 dx and I replace it with just du. And I take out the x squared plus x and I replace it with just u. So now I have my new integral. The integral of u du. Okay, so integrated. I add an exponent, divide by the new exponent. That's my integral. The only thing left to do is to actually replace u with what it equals. All right, and there we go. And I'm done. Now, a good technique to make sure that you're doing this correctly would be to derive. So if I'm checking this, so this is basically 1/2 x squared plus x over 2, right? I'm just putting the 1/2 in the front. I like it that way. So deriving this would mean that I'm deriving the whole thing, and I'm treating this as a u. So 2 times 1/2, that's 1. And then I lose an exponent. So let me go ahead and make myself more space. Oops. Okay, so 2 times 1/2 is 1, and then I lose an exponent. So x squared plus x, that stays there. That's the inside. That's my u. But I lose an exponent. And then I multiply that by the derivative of u, which is 2x plus 1. And then the c is a constant, so it becomes 0. So basically here I have what I started with. Maybe a little out of order, right? I can put the 2x plus 1 in the front, and then that in the back, just like it was given to me in the beginning. The same thing. All right. Next, example 3. I think this is the example. Yeah, for this example, I wanted to show you how to multiply and divide when you have a constant, a number that's out of place, and I used an equation that is just regular. So I need you to, on your paper, please, I'm sorry, there was a 3 here. I want you to ignore that 3, so scratch it out, white it out, whatever. Okay, so there was a 3 there, but it's not going to suit my purposes, and I'm sorry for that. Okay, so without the 3, figure out what is u and figure out what is du. So so looking here, I know that if I derive this, I get 3x squared. Now, this doesn't quite look like 3x squared, right, because you deleted the 3 like I asked you to. It doesn't quite look like 3x squared, but it's pretty close. So x cubed plus 1, that is my u. Okay, there is an exponent. It's to the 4th power. This is going to stay here. Okay, you're going to leave that alone. All right, du. Now, derive u. U is x cubed plus 1. So the derivative of that is 3x squared plus 0 dx. Now, this is an example of when your derivative doesn't look exactly like the rest of the function in the integral. Okay, so what I'm saying is this is this exactly. But the 3x squared, that is not in this problem exactly. Okay, the dx is definitely right there. And then the x squared is definitely right there. But what is missing is the 3. So I have to compensate for that because it has to be there. And I repeat, this is the 3rd time I'm going to say it. I asked you to erase the 3 because it didn't do me any good for what I wanted to show you in this example. So please erase the 3. Okay, so back to this. So I have to make up for the fact that that 3 is not there. And the way to do that is kind of algebraically. If I'm realizing that I need this 3 gone in order for this to work, I'm going to divide it away. And then whatever you do to one side, you do to the other. So now, when I'm ready to replace my equation or my expressions with u and du, this is a little twist. This is x squared dx, right? But now this is 1/3 du. Okay, so when I replace the x squared and the dx, it's not just going to be du, it's going to be 1/3 du. Okay, so again, dx and the x squared, so those are going to get replaced by 1/3 and then du, or you can even write du over 3, but this is, I don't know, this is nicer. And then the x cubed plus 1, that's going to be replaced by u. Now, integration rules. Oh, hold on. I forgot my limits. X equals 0 and x equals 1. Remember, those limits belong to x. Okay, integration rules allow us to do something with a constant multiple. So like that 1/3, if it'll make it easier for you, and most of the time it will, you are allowed, and I've done this before, we've done this before, you are allowed to take that 1/3 and pull it out of the integral. So now this is going to be 1/3, and then x equals 0, x equals 1, u du. And then you can just integrate the u without having to worry about the 1/3 till later. Okay, so integrate u, and so that means I'm going to add an exponent and divide by that new exponent. And then I am evaluating from 0 to 1. Okay, so before I evaluate from 0 to 1, I need to plug the u back in, or the actual original function. So 1/3. And see that 2 on the bottom there, right here? I'm actually, since I'm already done integrating, and that's just, it's being divided by 2, I can pull that out as well, right? It makes it easier, I think, anyway. So there's the 1/2. So now this is what I have. You don't have to. You don't have to pull this stuff out. But since we are so afraid of fractions, I think that it would help. Okay, so this becomes 1/6. U squared. U was originally x cubed plus 1, and then that's squared. And then you're evaluating it from 0 to 1. And I don't have to write x equals anymore because the x's are back, right? I knew I forgot something. Story of my life. It's really hard to talk and to do things at the same time and not forget something. Okay, and you probably noticed, hopefully, anyway. This 4, I totally forgot him. This should have gone here. What I said about the 1/3 still stands. So there goes a 4 also. So then when I added 1, this would have become 5. Oy vey. And then when I divided by the 5, right, this would become 5. And then what I said about pulling that number out, you could still do that. It's not wrong. It's just the wrong number. So that's 5. So I'm just fixing my exponents. Sorry. I noticed I'm like, this doesn't look like what I remembered. Okay, so 5, 5. 3 times 5 becomes 15. Not 2 times 3, right? 15. And then this beauty right here is still a 5. Okay, so not too much. It's just changing the, putting in the 4 and then getting 5s everywhere. All right, so I'm going to continue. Ah, baby Jesus. Okay, so I have to plug in 1 and I have to plug in 0. Thankfully, 0 is so easy to plug in. And 1 is also. So 1 cubed plus 1, so that's 2. 2 to the 5th power, 32, right? So 32 minus, plug in the 0. So 0 cubed is 0. 0 plus 1 is 1. 1 to the 5th is still 1. So we get, finally, 1/15 times 32 minus 1 is 31. So my final answer, wow, that looks just weird. My final answer is 31/15. Now for this one, because the integral actually has limits from 0 to 1, a good way to check, because we should not be dependent on our calculators, right? A good way to check to see if you got your answer correctly would be just to plug in the integral into the calculator, right? We should know. Math number 9. Okay. Next. Is it moving? Nope. Any day now, please? Oh, there we go. Example 4. Okay. Same idea. There's going to be a little error, or not an error. I know I messed up, but I mean, there's going to be a number that I have to compensate for. So 7x cubed, x to the 4th plus 3 to the 5th. Okay, so look at this and figure out what is u. What can I derive to get the other thing in the problem here? And I do see that x to the 4th, it does have a higher degree, right, than the x cubed. So that might be an indication that that's u. So x to the 4th plus 3. And then du would be the derivative of u. So 4x cubed plus 0 dx. Now looking up above, for x to the 4th, so this part right here is right here. There's a 5 here. Hopefully I won't forget it. And the dx is right here. And then the x cubed is right here. But the 4 is not. So divide by 4. So I have 1/4 du equals x cubed dx. Now you must be like, well, hold on. What about the 7? Okay, you can do one of two things. Once I replace the x cubed and the dx with just 1/4 du, and I replace the x to the 4th plus 3 with the u, I could treat what remains. Okay, so let me actually do what I'm saying here. So these are oops, there goes my pen. Okay, so once I replace these with, and I'll write it over here, 1/4 du, brain part. Okay, 1/4 du, and then I replace this with u to the 5th. The 7 can go right there. Okay, or you can pull out the 7 because it's just a number you're multiplying by. And while you're at it, you can pull out the 1/4 also. And that's what I'm going to do. I'm just going to go ahead and pull out both of these babies. So 7/4, right? 1/4 times 7. And then this is what I have to integrate. Okay, so u to the 5th becomes u to the 6th divided by 6. And then I am no, this is indefinite. Okay, so you can pull out the 6 also, right? And so I'll have 7/24. And then the u to the 6, I'm just going to go ahead and actually replace u with what it originally was. X to the 4th plus 3. And then this is a perfect example to go ahead and check your work. Integrate, or not integrate it, derive it, and see if you end up with the original integral. So yeah, and of course, because this had no limits, plus c, right? Okay. Next. Okay. Once again, don't be alarmed with the square root. It's not a big deal. If you want to rewrite this, I mean, recall the fact that a square root can be rewritten as just an exponent of 1/2. Okay, this is the same thing. Now look at this and figure out what is the derivative of what. Okay, so u it's going to be 9 minus x squared. Again, look at the exponents. They are your friend. This is a higher order exponent. It has a degree of 2, whereas this one only has 1. When we derive, we always lose 1. So that could help you figure out what is what. The derivative of 9 minus x squared is negative 2x dx. So looking at this, I can tell you that the dx is right here, right? The negative 2, not really there, but the x is right here. And then the u is this piece right there. So I'm going to go ahead and replace those things. And also, I'm going to be all like, okay, that negative 2 is not there. I needed it to be there. But since it's not, I have to compensate for the fact that it's not there. So now, when I replace, du is going to actually be negative 1/2 du, or rather, it's going to be together, and then x dx. Okay, so this is now x equals 0, x equals 3, and this is, I'm going to go ahead and write this square root as a 1/2 power. So u to the 1/2 power. And then I have to remember, oh yeah, the negative 1/2, and then my du. All right, I want to stop here for a second. This section was called change of variables, keeping it all about u. This is the other way to do it, and it's basically the same idea. It's just that you're gonna work with u all the way until the end of the problem. And this only works when you have limits, for a definite integral. And this is how I'm going to do them all from now on. I'm always just gonna keep it all in u. And if you like the other way, you're more than free to do it that way, but that's not how I'm gonna do it. To keep it in u, the issue are the limits. Okay, the limits, remember I'm like, okay, so we have to remind ourselves or keep in mind that those limits belong to x. Well, there's a way to make them belong to u. And it makes it easier to integrate, and it makes it easier to plug in. So, all of this stuff aside, what you do is you take the limits that are there, 0 and 3, and you plug them in to u. So I'm going to have to take some space because I only have space down, not across. So when x equals 3, and this is the upper limit, and I like doing the upper limit first because I don't want to keep it, I want to keep it in the same order, and you'll see when I'm done. So when x equals 3, right, what does u equal? So here's u. U is 9 minus x squared, plug in the 3. So 9 minus 9, so it's 0. So now my upper limit, because remember the 3 was the upper limit, my upper limit for u is 0. So then when x equals 0, that's my lower limit, u is 9 minus 0 squared, so that's 9. So my lower limit for u is 9. Now you must be like, well, hold on. The lower limit is bigger. Yes, and the reason for that is um, because I'm now working or trying to work with you. So what I'm going to do is I'm not going to have to worry about x equals 3 and x equals 0. And I'm not going to have to plug 9 minus x squared back in at the end. I won't have to do that. And that's why I like this way better. It's more straightforward because you don't have to do things at the end. You just complete it. If you do all of this at the beginning, you could just complete your integral. Okay, so I'm going to continue my work in purple, and I'm going to do it down here. That's supposed to be purple. Okay, there we go. So now my integral, I'm keeping it all about you. So my upper limit is 0, my lower limit is 9. I don't have to write x equals because it's no longer for x. These are values for you. My 1/2, you know what? I'm going to go ahead and pull that out to the front because it just makes my life easier. So the negative 1/2 is right here, sitting in the front. And then u to the 1/2, and then du. So this is what I'm going to integrate, and I'm not going to have to plug u or x, 9 minus x squared back in. I'm not going to have to do that. And I have new values, so I can just evaluate my integral with 0 and 9, and I don't have to worry about 0 and 3 or whatever the numbers were. Okay, so integrate it. U to the 1/2. So u, add an exponent, and then divide by my new exponent. And I'm evaluating this from 9 to 0. The upper limit is lower than the lower limit. That's okay. Okay, so negative 1/2. All right, plug in 0. So 0 to the 3/2 power is 0 times 2/3 is still 0. Minus, and then I'm going to go ahead and plug in the 9. And so, let's see, 2/3, and then 9. And the top part means cubed, but the bottom part means square root. So I'm going to do square root of 9 cubed. Okay, so let's see here. So this is going to be negative. Now the square root of 9 is 3. 3 cubed is 27. So 2/3 times 27. Okay, so ooh, I can cancel out. There's 1 here, and then there's 9 of them here. Right. So negative 2 times 9 is 18, divided by 1. And then times negative 1/2. That's a big fat old positive, and positive 9. And there's my answer, and this would be a good one to check by the calculator, math, and then number 9. Okay. Example 6. There was something wrong with example 6. I don't know where I got this question from, but the domain had an error. So I had to change it slightly so I could actually find some kind of answer. And then I plugged that in the calculator, and it still gave me a domain error. But it's no big deal. We can use it for good practice. So change the exponent to a 2 rather than a 3. And okay, so the dx is on top. That's no big deal. Okay, if you could just get over the fact that the dx is on the top and just see it this way. It's 1 over 8x minus 1 squared, and then here's the dx. Okay, this is the same thing. This always makes people stumble. I don't know why. Okay, so same thing. All right. Figure out what is u, figure out what is du. So obviously there's only one thing here, 8x minus 1. So that's my u. My du would be the derivative of that, so that's 8 dx. Well, looking at the top there, well, I have my dx, right? I don't have my 8, so I'm going to have to compensate for that. Right? So divide by 8, and then I'll just put 1/8 right there. And then, obviously, u is this part right here. Okay, so if you rewrite that, now with u and du and whatnot. But then, because I don't want to have to switch back and forth, I'm going to keep it all about u. So I need new limits. I'm just going to scroll down here a little bit. Okay, so u, I'm going to plug in the 2. So 8 times 2 minus 1. So 16 minus 1 is 15. And then I'm going to plug in the negative 1. So 8 times negative 1 minus 1. So it's negative 8 minus 1 is negative 9. So there are my new limits. So 15 and negative 9. Okay, notice how I do the upper limit first and then I do the lower limit. So I know that this is top, this is bottom. Okay, and now 1 over 8x minus 1, that's going to become 1 over u. And oh yeah, but 1 over u, how can I rewrite that? I just want to go ahead and save myself some steps. U to the negative 1. And then the 1/8, I like those nice little fractions. I like them outside. So 1/8 right there. And then du. Okie doke. All right, so I have my new limits. I plugged in the u, du, etc. I don't have to deal with x any longer. I don't care about 8x minus 1 anymore. Oh look, I almost messed up again. Oi. The 2. It's a 2. Oy vey. Okay. So I don't care about 8x minus 1 anymore. All right, so 1/8. There it is. U to the negative 2 power. Okay, so when integrating, you add an exponent. So now this is going to be u to the negative 1, but then you divide by the new exponent. So dividing by negative 1, I'm basically just making this function negative. And that negative is the same thing as that 1/8. I can just put that baby outside. And that way I don't have to worry about it anymore. So let me put the 1/8 a little closer. 1/8, and here's a nice little negative. And I don't have to worry about it anymore. Okay, so add an exponent, divide by it, and that's why I put the negative 1 outside, basically, right? And I'm evaluating this from 15 and 9. Okay, so negative 1/8. Plug in the 15. So basically 1 over 15 minus 1 over 9. And, okay, negative 1/8. Alrighty, let's see. 15 and 9, they have the number 45 in common. So 1 over 15 becomes 3 over 45. And 1 over 9 becomes 5 over 45. And by changing that one little number, these numbers got really pretty or really nice. 3 minus 5 is negative 2 over 45. And then we just multiply. Oh, wait. Oops. Negative 9. I just saw it. Negative 9, so that becomes positive. Oi. Positive. 3 plus 5. Oh, look at that. It's 8. Forget about... Okay. Okay, there you go. So negative 1/8 times 8 over 45. These 8s actually just go bye-bye. 1 and 1. Cross simplify. So negative 1 over 45. And there's my answer. Go ahead and try it. Don't try A. This is going to be the new A. The old A, I don't know what was wrong with the old A. These are problems from last year, and I don't remember. I just know that I ended up with a square root of a negative number. There's no imaginary numbers here. Thank goodness. I hate imaginary numbers. But don't do A. Just do B. Okay? I'll write the answer. All right. So this is what I have so far. I went ahead and replaced the limits with the limits for u. Right? I plugged in pi to the 6, and I plugged in 0, and I got pi over 3 and 0. I integrated, and now I'm going to need the unit circle. So there's my unit circle. So 1/2. And then negative cosine pi over 3. Cosine of pi over 3 is 1/2. So negative 1/2. Plus cosine of 0 is 1. So 1. 1/2. Negative half plus 1 is just a positive 1/2, right? So then I just get 1/4. And that's my answer. Okay. Be ready for class. For whoever watches the video, be ready for class.